Welcome to Verilog HDL subject. So today we'll start with the module 3, that is gate level modeling. Okay. So already we know. So what is basically the gate level modeling is? It is one of the HDL modelings. So as we know, there are the 4 different modelings are there. So uh, as as it is as we are dealing with the first level gate level modeling and data flow modeling, okay, and behavioral modeling and the switch level modeling. So as these modelings are the different ways in which we will write the HDL code. Okay, so gate level, data flow, behavioral and switch level. So very basic level is the switch level. Okay, so in switch level we will write the code in terms of the transistors, means we will have the circuit, the whatever we want to design, whatever we want to model, or whatever we want to write a code in Verilog HDL. Okay, so that input in the switch level it will be in terms of the transistor. So there will be a transistor circuit, so that we are testing, that we are modeling, that we are writing the code. Okay, so in the Verilog, so that is very basic level that we call as a the switch level. Okay, the next one after the switch level, then it will be the gate level. Okay, so in the gate level, so as I said, so in the gate level the input will be in terms of the logic gates. The input will be in terms of the logic gates, means whatever the design we want to write RTL code or Verilog code, so the input will be in terms of the digital circuit, means logical circuit. So that is in terms of gates. Okay, so in form of the gates we will have the inputs, so that we will model in the Verilog, using the Verilog. So after that, if we take the behavioral modeling, so in the behavioral modeling it will be in terms of the input will be in terms of truth table, or we call as the algorithm. Okay, so the steps wise, the algorithm, the way in which we want to do the design. Okay, or in the form of the, which basically it will describe the behavior. Okay, how the design should be. So that is maybe in the form of truth table or in the form of algorithm. Okay, the last one means the one more is as the data flow modeling. So in the data flow modeling, as earlier also we know, so it is with respect to the Boolean function. Okay, the Boolean function. So whatever design in the form of Boolean function if we have, then we can realize using the data flow model. Okay, so like this there are 4 basic the different modelings are there. The first one as we are seeing here is the gate level, means in the input should be in the form of the logic circuit or logic gates. Okay, so as we move on in this module, so the contents will be like the modeling using, means gate level modeling using, means the Verilog has the, okay, the basic primitives. Okay, the Verilog gate primitives, means modeling will be using basic Verilog gate primitives. Okay, as I said, we have the input in some of gates, so that gate itself means we have the predefined keywords or primitives. So by using those we will write the RTL code. The next one, in that case, there are 2 types of primitives. One we call as AND OR, and one more we call as buff not type gates. Okay, AND OR type gates and buff not type gates. Then which are the different delays we will use, like rise, fall and turn off delays, and in that again in turn we have the minimum, maximum and typical delays. Okay, so these all things we will see in the gate level modeling. Okay, let us start with the first one, the gate types. Okay, so as we know, we have the basic gates like AND, OR, NOT, NAND, NOR, MUX, XOR, XNOR. So these are the basic the gates already what we know. Okay, so here the same thing what he is talking here, the gate types. Okay, is the same thing. In this modeling the circuit is described in terms of gates. Okay, so what is the gates, like AND OR, okay, AND OR XOR. So the basically the design will be means in Verilog it is designed in the form of gates. Okay, and Verilog supports, as we said in the previous, Verilog supports the basic logic gates as predefined primitives. Okay, as predefined primitives, we will the Verilog will support all the basic gates. So as these basic gates is divided into two types, so one is and or, and one more is buff not. Okay, so and or gates is one type, and buff not is a one more type. So basic gates is divided into these two types. Okay, so now so as it is the two types of basic gates, you will see the first one, and or gates. Okay, so and or gates, in this and or gates, it will have one scalar output. So as we are saying, one scalar output and multiple scalar inputs, means whatever may be the gate. Okay, suppose if it is X gate here, okay, so there will be one scalar output. Scalar in the sense, so there will be no vector, so one bit output. Okay, scalar means it is not vector, it is a single one bit output and many scalar inputs, so many one bit input. Okay, like maybe 1 2, like n inputs, but each of single bit. So that is what the meaning of multiple scalar input. So any gate, okay, any gate will have the multiple scalar input and one scalar output. So that's what the meaning here. And whatever in that, the first terminal in the list, okay, suppose I am using any some X gate, I am using the parameters here, I am mentioning the parameter in that, the first terminal of the gate is output, should be output, and other terminals are inputs. Means if I specify any gate here, okay, in the parameters, the first terminal, the first parameter will be output, next it will be followed by inputs here. Okay, this is what the meaning here. Okay, so in the parameter, always first will be output, next will be inputs. So now, as the gate has multiple inputs and one output, means both are scalar, and the first one is output, next is a inputs, and the next one, what are the and gates will cover, and or gates type will cover. Okay, as we mentioned here, means and, NAND, or, NOR, XOR, XNOR. Okay, except the NOT gate. So all 6 gates will cover in the buffer, or sorry, and or gates, and, NAND, or, NOR, XOR, and XNOR. Okay, so these are the 6 types what we are covering in the and or gates. Okay, so the next one, what are the symbols? Okay, the symbols for these basic gates. The symbols for these basic gates and or type gates is, so as we know, the and symbol is this, or symbol, XOR, NAND, NOR, and XNOR. Okay, so all these things we know basically, but here once again we are revising, it's there here. Okay, so symbol for and gate, and here all the gates have two inputs. All the gates have two inputs, like I1 comma I2. So these are inputs, and out is mentioning as a output here. Okay, the output signal name is out, and input signals are I1 and I2. Okay, so these are the symbols for and gate, or gate, XOR, XNOR, okay, NOR, and NAND. So as we know, so these are basic and or XOR, and NAND will be just by putting the bubble of that. Okay, and compared to or, the NOR will be just putting the bubble of that, and XOR also by putting the bubble it will become the XNOR. So it is basically reverse of, so NAND is reverse of and, NOR is reverse of or, and XNOR will reverse of XOR. Okay, so these 6 gates are the type of and or gates, and here we are considering only the 2 inputs. So like this, the gate may have any number of inputs, like I1, I2, like IN. Okay, usually it is 3 bit input, means 3 inputs, 4 inputs, 5 inputs, so like that, 8 inputs, 13 inputs, so like that the different gates will have the different inputs, but always the output will be one only. Okay, this is regarding the and or gates, means which are the gates what it will cover here. The next one, okay, I have the gates now. How to use that in the code? Okay, so I have the circuit. For example, okay, I have the circuit like this is AND gate, okay, and this is XOR gate, means A and B, and this is sum and carry, okay, or XOR, okay, it's OR gate. If you take okay, any, it's not means will not go for the particular any code or like that, any circuit, okay. Suppose one is OR gate and one is AND gate here, okay, or an AND, okay, and here XY and here XY, okay, and some F1 and F2, okay. So suppose this is a circuit, the two inputs are there and two outputs are there. If this is circuit, how to, the input will be like this, how to write a code. So these, whatever the gates what we are mentioning here, so these gates directly by using the predefined primitives or keywords we can write the code. So how to write is, this is what we call as the gate instantiation. Gate instantiation means we are calling the function. Instantiation means we are calling the function. So here, that's what the gate instantiation of AND or gates here means. The first, what is the method here? Okay, first we need to declare the inputs and outputs, okay. So as we are seeing, so wire out and in one and into, so all are the signal type, means all are wire here, okay, all are wire. And here, as I told, it is AND gate, so IN1 IN2 are inputs and out is a output, okay. As we are seeing in the parameter, first always you should write output and these should be inputs here, okay. So what is the method here is, first is we need to use the primitives, predefined primitives. For AND gate, as the name suggests, so the first is a, for AND gate we have the primitive AND, for NAND gate we have the primitive NAND, for XOR gate we have the primitive XOR, for OR gate OR, for NOR gate NOR, for XNOR we have the primitive as XNOR. As the name suggests only, AND gate and NAND OR NOR XOR XNOR. So these are the primitives, means predefined values, predefined keywords, we can't use other one. For AND gate, this is the format, means we need to write AND primitive first, then A1 they have written, A1 is a, we call as instance name, okay, instance name, any name you can write, okay. We can write your name, okay. So we can write any A0 A1 or M1 M2, any name we can write, that we call as a instance name. This is a primitive, this is a primitive. And after this, this is the parameters or the list of inputs and outputs, okay. In the list of inputs and outputs, always first we should write input output, then we should write the inputs here. This is what they have written here, okay. Similarly, if the circuit contains NAND gate, then it will be NAND, then instance name, inputs and outputs. Similarly, for OR instance name, inputs and outputs, NOR instance name, inputs and outputs, and XOR, okay. It is similarly like as we are seeing in the previous slide, okay. The same inputs are connected to all the gates and all the gates having the same output, okay. So just it is for the showing how to write, these are the, if these are the inputs and outputs, how to write the code, okay. So here AND gate, NAND gate, OR, NOR, XOR, XNOR, and this is the, what is the format is keyword or predefined word or keyword. Then after that, okay, after that instance name, after that the parameter list and semicolon, okay. And first is keyword space instance name space and the list semicolon. So this is the format what we need to follow for each word, Okay, suppose as he has mentioned, if there are more than inputs, keyword will be the same, NAND. It is not, the keyword will not different. Keyword is NAND, instance name you can give anything, and out is one output will be there and three inputs will be there. Okay, so this is what we call as the gate instantiation. Means if you want, if you have the circuit with respect to these basic gates, okay, so then with respect to these basic gates, then we can have the AND, instance name and parameter list. One single line is enough to write the, means how many gates are there, so that many instances will be there. Okay, so this is for 3 input. And one more thing, instance name is not compulsory, means and we have not mentioned any instance name and outputs and inputs, so it is a legal. So this we can use only when only one gate is there. If there are same two gates are there, for example, if there are two AND gates are there, okay, we have, if we have the two AND gates, if we have the two AND gates, then we need to differentiate between the first AND and second AND. So that we can done with the, we can do with the instance names. Okay, so because of that the instance names are required, or we can give any particular name. This is N1, N2. I want to differentiate, okay, which gate is what connections. So then in that case we can use the instance name. Okay, but keyword will not change with respect to instance name, whether it is mentioned or not, or how many inputs, the keyword will not change. Keyword is same for whatever may be the inputs what we are connecting. Okay, so this is how to call the function, or we can call as how to instantiate the gates. Okay, the next one. So then what is a truth table? Okay, so what is the truth table? It will be there, means, so we are considering here 2 input and 1 output. Okay, so already we know in the data types, okay, in the data types we know that what is the basic data types, 4 values, 0, 1, x and z. These are the 4 data types or data values. The value set what we are using is 0, 1, x, z. Okay, the strength is different. We have seen 8 types of strength, that is pull, weak, okay, supply, all those things. Okay, weak pull up, so those strengths are different. Okay, but here what we are talking is only the value set. So what values we are using, okay, so those values we need to use here. Okay, means there are 2 inputs, so we are talking only about one thing. If you take about one here, okay, so there are 2 inputs like I1. Okay, if you take like this, okay, so okay, here if you see the one truth table, if you see like this, okay, so I1 is one input, I2 is one input and output is only one. Okay, so now I1 can be 4 values 0, 1, x, z, and I2 can be 4 values 0, 1, x, z. Okay, in that case if we have the 4 values here, 4 values here, and what may be the possible output. Okay, so the same thing what we need to see here for AND gate. Okay, for AND gate, okay, for AND gate, if I1 and I2 both are 0, 0, the output is 0 corresponding. Okay, it is like for this input and this input, so this is the output, and this input and this input, this is the output, and this corresponding here, and here this is. And if you take the second one, this like this, so it is basically the horizontal, okay, this vertical lines and the horizontal lines. Okay, this is what how we need to read. Okay, so okay, let us take here first OR gate only. If OR is 0, this is 0, 0. First we need to, before this we need to know the basic truth table of the gates. Okay, if you take the OR gate, if you take the OR gate, if A and B are the inputs, okay, so what will be the Y here? If it is 0, 0, 0, 1, 1, 0, 1, 1. Okay, for OR gate this is 0, 1, 1, 1, means if any one of the input is 0, the output will be, sorry, if any one of the input is 1, the output is 1. This is the basic OR gate. truth table. Okay, similarly if you take the AND gate truth table, okay, A and B, and Y is the output, and 0 0 0 1 1 0 1 1. If you take like this for AND gate, 0 0 0, and where if all the inputs are high, then the output is high. So this is for AND gate. The same thing, before doing this one, we need to know the basic truth table of the gates. Okay, for AND gate, 0 0 output is, if any one of the input is 0 for AND gate, all the outputs are 0. So this is 0 here. Similarly for this one, if any one of the input is 0, the first row is 0. If you come to the second vertical line, 1 with the input I1 is 1 and I2 is all these 4, 1 into 0, 1 into 0 0, 1 into 1 1, 1 into x is x, 1 into z is x. Okay, means 1 into x means don't care, 1 into x is x only, don't care, we don't know. Even 1 into z, okay, so z is high impedance, so because of that we don't know what may be the value, so that we can call as a x. Means here you can observe this truth table, none of the output is z, it is only either 0 1 or x, means 0 or 1 or don't care, the outputs are 0 or 1 or don't care. Okay, so if any one of the input, means input itself is x, if I1 is x, I2 is any value, x into 0, so 0 into any value is 0 only, x into don't care into 1, don't care into don't care, and x into z is x. Similarly z into 0, that is 0, z into 1 x, z into x x, z into z x. That is for AND gate. Similarly if you take OR gate here, so 0 plus 0 0, 0 plus 1 1, 0 plus x x, 0 plus z x. Okay, so there is no output as z, either 0 1 or x. Similarly if you take I1 as one input, I1 as 1, and if you take these values, 1 into 0 1 plus 0 1, 1 plus 1 1, 1 plus x 1, 1 plus z 1. So also we need to know the Boolean postulates. Okay, so 1 plus x equal to 1, whatever may be the value, 1 plus x means it is 1 only. Okay, so these postulates we need to know, and we need to write the, means these postulates plus the truth table of OR gate. Okay, and similarly x, this one, x plus 0 x, x plus 1 1, x plus x x, x plus z x. Okay, then z plus 0, it is x, because we don't know what is the value x, z plus 1 1, z plus x x, and z plus z, it is x, means don't care. Okay, similarly for XOR gate, 0 plus 0 0 XOR 0 0, and 0 XOR 1 1, 0 XOR x x, 0 XOR z, it is x. Okay, so like this we need to see for all the gates. And one more thing, so we need to know, while writing this one, we need to know truth table of the basic gates in the sense that is AND gate, OR gate, and XOR gate. If you know these things, then it will be reverse here. Okay, as we can see one of the thing, okay, if you see OR and if you see NOR, it is just reverse of that. Okay, so here wherever 0 is there, you write it 1, and 1 0, and wherever 1 is there, you write it all 0. Wherever x is there, it will remain same. Okay, so it is just the verification. Okay, so like this, if it is XOR, so XOR will be only the reverse of wherever 0 1 1, wherever 1 is there 0, wherever 0 is there, it is 1. So reverse of that, wherever x is there, it will remain same. Okay, so like this we can verify the NOR, XNOR, and the NAND truth tables. Okay, so basically we should know the truth table of these gates, then we need to write. If these are correct, then it is reverse of that we can write down. Okay, so like this, so these are the truth tables. So till now we have seen only truth table with A and B, like 0 0 0 1 1 0 1 1, means only zeros and 1. we are not seen with x. So that's what we are seeing now in these two tables with x and z. What are the outputs? So as I said earlier, we need to remember here, okay, so none of the outputs are z, okay, and we need to see if anything with respect to x means it will always, most of the cases it will be x, except the 1 plus x 1 plus x is 1. So we need to know the postulates and we need to know the truth table of the basic gates, then we can write down the these things, okay. These are truth table with 0 1 xz, okay. So in the exam also, if they ask truth table means we should not write only 0 0 0 1, we need to consider all these values with respect to this module, okay. So this is regarding truth tables for and or types, okay. So in the next class we will see about buff and not gates, okay. So today we have seen here what is gate level modeling. So it is one of the four different types: switch level, data flow level, behavioral and gate level. So in the inputs in gate level, the input will be in terms of logic gates. So that logic gates, there are two types: and or and buff not. And today we have seen and or, and these and or we will use by using the primitives, what we are the mentioning here, the primitives, and the format how to use the primitives is, and here what we call as the instantiation, okay. This is how we can use the realize the circuits by using the instantiation with respect to the basic types. And these are the truth tables what we will get the outputs with respect to 0 1 xz values.